So then let's discuss a little bit on what to do if we have a digit boundary condition but with a non-zero but not zero. So a completely different. What if I have u equal to ub at the boundary? You can repeat the exercise we did on the last slide. You can find out there is no way I can modify the linear functional or bilinear functional to get a match on this type of boundary condition. Okay, so we have to resort to restrict the space. And restricting the space actually doesn't completely work here because I'm restricting the space of the solution such that the space of solution has to satisfy a non-zero boundary condition, which makes the space no longer a linear space, right? For a linear space to be a linear space, the zero element has to be in the space. So instead of a linear space, I get to an affine space. So I have to define an affine space where the solution lives in. But I still have a linear space that the test function lives in. The test function is remember we are projecting the residual of the Poisson's equation or any differential equation into a linear space, right? Now we were projecting the linear space, and basically the test function can be anything that constitute a difference in two elements in the affine space. A good example is a projection. So let me say, okay, what if I project a function f to xh with b? So this is defined as any function f within the space xh, and let me say any u, project any u in the xh and u equal to ub at the boundary. So this is a restricted version of xh. So I have a xh that is a lower dimensional function space where f lives in the higher dimensional function space, and I want to project this f into the space, into the affine space, no longer linear space, into the affine space that is not only lives in the linear space xh, but also satisfies a non-homogeneous boundary condition. What I'm doing is saying that, so let's say fh is the projection, is the projected f. What makes fh the projected f is the fact that fh is the closest element in the xh to f. Or in other words, f minus fh is orthogonal to any u minus fh for u also in this xh. Right? Remember our derivation of the shortest distance is that the norm f minus fh and f minus fh, so that this is a notion of the distance, is less or equal to any u minus let's say f minus u and f minus u. I mean, this angular bracket are like basically inner products, right? So if you derive from that, you are going to derive the fact that f minus fh and u minus fh has to be equal to 0 for any u. Okay, and if you take u minus fh to be really the test function that f minus fh has to be orthogonal to, that means u minus fh has to be in the homogenized version of that xh, or the statement is u minus fh has to be in the space of u minus fh. Of course, it has to be in the xh because xh is a linear space, and u minus fh is equal to what at the boundary? Equal to what? 0, yes, because both u and fh has to satisfy the same boundary condition. Okay, so the space xhb is the subspace. Now, I mean, I shouldn't call it subspace because it's no longer a linear space. It's the affine space within the xh, within the bigger space xh, that satisfies the same non-homogeneous boundary condition. And the projection works and the projection is projecting any f to this space, and the projection can be tested by the orthogonality of f minus fh to any difference, to the difference between any two vectors in this affine space. And the difference between any two vectors in the affine space is an element in the now linear space that satisfies the homogeneous version of the same boundary condition. Okay, or the statement becomes, the finite element statement becomes the bilinear form of u v equal to L of v for any v in the xh0, the homogeneous version, where u has to be in xhb, the inhomogeneous version of the space. So that's the compromised way of specifying a boundary condition that cannot be specified the natural way, like the Dirichlet boundary condition we have for the Poisson's equation. Okay, so this basically tells you how to for differential equations, how to derive the weak form, generally what a weak form is, how to derive the weak form using the differential equation, and also the boundary conditions. And for all kinds of different boundary conditions, you can either do it the natural way, or if that doesn't work, do it using the essential way.